Let's use an example to connect what we have learned so far. In this A, it has 3 rows, 4 columns. Do the 4 columns fully span R3? 4 columns theoretically are larger than 3, but this only means that 4 columns cannot be all independent. This doesn't mean we can always find 4 columns that spans R3. It's very different. So to find or to check whether they can span R3, we need to find at least 3 independent vectors. Not at least exactly 3 independent vectors. So let's perform the ultimate skill in this short course, Gaussian elimination. And if we do this right, A will turn into 1, 3, 4, 1, 0, minus 2, 0, and 0, 0, 0, 0, which means there are 2 pivots, which forms a rank of 2 in U. So the number of independent columns is only 2. This means that they can at most span R2, not R3. So only R2 in this case. Yeah, if you check the each original row without original columns without performing Gaussian elimination. Yeah, similar, because the first and the fourth columns are identical. The first and the second column leads to the third column. This means that these are like redundant information. All the informations are given in the previous 2 columns. So yeah, that's why the first and the second columns are considered as pivots. Yeah, so no, the 4 columns are never independent in R3, never. So is there vectors in the null space other than the 0? Yeah. Yes, because we can have 2 free variable which is further substituted by the pivot variable. In particular, minus 2x3 minus 2x2 plus minus 2x3 equals 0. So x3 can be expressed as minus x2 and x4. Oh no, x3, yeah, x2 can be expressed as minus x3 because the purpose is to make pivot be the combination of 3 variables, and x1 will be x3 minus x3 minus x4. So the total null space solution can be x3 minus x4 minus x3, x3, and x4, which means x3 times 1 minus 1, 1, 0, plus x4 times minus 1, 0, minus 1, 0, 0, 1 is the null space vector. When we express the null space vector, we can see the rank of the null space is R2, and the basis for the null space is identified by 1, minus 1, 1, 0, and minus 1, 0, 0, 1. Yeah. We use the subset to call subspace. Yeah. There are parentheses, the meaning subset, but more importantly, this subset is a subspace, and we express the subspace by identifying the vector in the basis. So the dimension for the column space is R2, which is the same as the rank of A. And how about the basis of the current space? Yeah, a common mistake is to check the pivot columns in U. So the current space could be incorrectly expressed as 1, 0, 0, 3 minus 2, 0. No, this is not the basis for current space. An obvious mistake is the last entry, 0. How can 0 be the last entries in the basis? It means the linear combination of these vectors would be all the vectors in the current space. But if the last entry is 0, how can you produce something other than 0, like 1, 3, 4, 1 here? So no, we cannot produce those vectors if the basis is 0. So this is not the right way to find the basis for current space. And the basis of the current space is found by tracing back these pivot columns to A. My point is, yes, we see pivots and pivot columns from U. That's easier. But when this comes to the basis for current space, these columns have to be traced to A, the original A, and find the 1, 1, 1, and 3, 1, 3 as the basis. That's the correct basis for the current space. But why the basis is found by tracing back U to A? Remember, when A is reduced to U, all the procedures we did are based on row manipulation, and row manipulations won't generate new information. So the goal of U is to tell us the independent structure, which will be the same as the independent structure in A. So if the two vectors in U are independent, including the first one, 1, 0, 0, and the second one, 3, minus 2, 0, the associated columns in A must also be independent. In other words, from U, we see that the last columns and the third columns are dependent from the first and the second. Yeah. So in A, the last column and the third column and the fourth column must have something to do with the first and the second. The independent structure won't be affected in Gaussian elimination, yet the number has been changed. So you cannot use those independent columns in U to find something as the independent columns in A. So next question. Yeah. This slide shows some smarter way to check a matrix, and it uses that important statement. The number of independent columns will be the number of independent rows. So consider 1, 1, 2, 2, 2, 5, and 3, 3, 8, which is considered as the basis for R3. And if they are the basis for R3, this is just another statement about checking whether they are independent. Because there are already 3 vectors, you can never have R3 using only 2 vectors. No, the number of vectors is insufficient. So to serve R3 as a basis, you must have at least 3 vectors, and you must have at most 3 vectors too, because in basis you cannot have dependency in it. So it's just to ask, are they independent? Are 1, 1, 2, 2, 2, 5, and 3, 3, 8 independent? I designed this vector because 1, 1, 2 plus 2, 2, 5 will be 3, 3, 7. So it would be obvious if I assign 3, 3, 7 as the last vector, and clearly 1, 1, 2, 2, 2, 5, and 3, 3, 7 are dependent. If I change the last entry purposely, I add it by 1 and make 7 be 8. Can I have a C1 times this plus C2 times this? That gives 338. Is this even possible? 1 and 1 gives 7 for the right hand side, the last entries. So is it truly possible if I add the last entry by 1 and get some C1, C2 as solutions? Because this is like two vectors be synthesized into another three-dimensional one. So can I actually do that? Should I do that? Should I try everything I can to solve C1 and C2? No, I don't have to. Because if I put them into a matrix, 1, 1, 2, 2, 2, 5, and 3, 3, 8. Yeah, I don't see whether the three columns are independent, but I can easily see the first and the second row are dependent. The first and the second row are all 1, 2, 3. This means that I have two dependent rows, so I must have two dependent columns. The number of dependent columns, the number of independent columns will be the number of independent rows, will be the rank of a matrix. So no, they cannot serve R3 as a basis because I have at most two useful vector. One must be dependent from the other two vectors. Similarly, for the last question here, what number Q would make A to have two independent columns? It needs independent columns, right? So what Q here would make it independent? Can we do this fast? Or should we use Gaussian elimination and finally check the last entries after some manipulation B0? Yeah, first of all, the number of independent columns must be the number of independent rows. The second row already takes one independency. You can not have something other than 0 to make the three rows be combined into 0. This is the only non-zero element where the first vector, the first row, and the third row all have a 0. So to make the linear combination of three rows be 0, the second row already takes 1, 0, which means they already take one independent information, and if there is only one independent column left, the first and the third row must be dependent. 1, 0, 2 as the first, so naturally 5, 0, 10 will be the third, so the third row is 2 times the first row. Yeah, this is why matrix attracts me. You can see the information in columns from row. When we generate a matrix based on only column, you already determine the structure of row. In other words, you generate A, but A transpose also tells you something about A. So now this short course has lasted for about 2/3, and it's the time that we formally find the four fundamental subspaces: row space, null space, column space, and then null space. There are two ways to identify the basis of a subspace. The first way is to find it by spanning. You have some vectors and the span of these vectors form a subspace. For example, row space and column space are found by this. In contrast, some spaces are found by constraints, like null space. And the last one, left null space. They are found by constraint. But we work with the 4 subspaces with only one technique, which is the ultimate one throughout this short course, Gaussian elimination. And we can connect the subspace in U to rows in A. So consider this case. A, 4 columns, 3 rows. And by doing some Gaussian elimination steps, we finally get the U there. So from U, what does the row space mean? And yes, from the introduction about space, now perhaps you already knew the row space means the subspace spanned by all the rows. The subspace spanned by all the rows called the row space of A. Similar to current space. The current space is defined based on the subspace spanned by all the columns. For such an A, the way to find the row space is C1 times the first row plus C2 times the second row plus C3 times the third row. You name those C, you find the whole subspace. But this is not the cleanest way to find a subspace. To fully define a subspace, we need basis. Basis is the ID for any subspace. So from U, we can first see pivots, the pivot columns. And the row containing pivots are also independent. We work toward column, but columns tell us something about the row. This further means that the first row in U and the second row in U are independent. So the basis can be found by 1, 3, 3, 2, 0, 0, 3, 3. That's the basis for the row space. And perhaps you are wondering, you ask about A, and why can't I see U? And why can't I see A from U? Should I give the independent rows in A like this one? Because all we need from U is to tell the independent structure. And theoretically, U only tells us the first column and the third column are independent, or the first row and the second row are independent. So shouldn't I trace back to A and see 1, 3, 3, 2, 2, 6, 9, 7 as my basis? How can I take those independent rows in U and consider them as the basis? Yeah, it's true that 1, 3, 3, 2 and 2, 6, 9, 7 are my basis in row space. This is true, it's correct. But it's equally true that these columns are the basis for the row space, because when I get U from A, the only steps I did are row operation. I multiply some rows by a certain number and add it to other rows, right? So all these multiply something and add to some other rows is linear combination, and linear combination won't generate something new. So when I make A be U, everything in U is the same as everything in A. Yeah, it will be exaggerated if I said everything in U be everything in A, but the information in the row tells the independent structure in U would be the same as those independent rows in A, as the only thing leads A to U is row operation, multiplication and addition. So no new information at all. But columns are not. When you make A be U, rows numbers in columns are different. Only row preserve the information because we performed only row manipulation. Okay, and the basis for the row space is found by in either case. And recall what I just said earlier, there could be more ways to identify a basis for a given subspace. Basis is not unique, but the dimension is unique for a subspace. The dimension is R2 in this case. We denote row space not by R parentheses A because I just said that it's another way to call column space, range. Yeah, so we need a new rotation. We call row space the column space of A transpose. Yeah, that's smart because row is the when you transpose A, column becomes row becomes a column. So the column of A transpose is the row of A. We use this notation to call row space the column space of A transpose. Next one, null space. Yeah, we already see the null space. A Gaussian elimination won't change the solution of X if B equals 0. So the X that makes AX equals 0 would be the X that makes UX equals 0. Dimension of null space is the number of free variable, n minus r. From here, I would like to clarify the dimension of row space as a subspace and the dimension of the vector in row space. The row space vector is like 1332, 0033, or the linear combination void. So each vector is from R4 or Rn for a general n by n case. Similarly, the null space produce also Rn because if A is n by n, x must be n by 1. So each x belongs to an Rn space. But the subspace of a null space is something else. You have to find the basis and check the number of vectors in the basis so that you can see the dimension for this subspace. And the dimension for the subspace is n minus r. So in terms of a general case, how about the dimension for a row space? Yeah, R2, I get it. But if in terms of a general sense, R, yeah, it would be the rank serving as the dimension for this subspace RR. And one is RR, the other is Rn minus R. N minus R plus R happens to be the biggest space for this vector Rn. And this is not a coincidence. Yeah. In the last section, we'll formally talk about it. You can see the information in null space from row space. Row space and null space are like bundled. They fill out the whole Rn. One take R, one take n minus R. Another induction from it is, if I have only null space basis, I don't have to write down those row space at all. I can see everything from row space, from the null space. Yeah, it's like I can see the information of column from the information of row. And now it's something else. I can see the information of row space from the null space, or vice versa. Yeah, I can tell the information in null space from only the row space, because row space and null space can be combined and fill the whole Rn. They can span the whole Rn, but one takes the R part, the other takes the n minus R part. Next one, column space. Before we find the basis and the dimension of the column space, let's check column space in the vector level. Each vector is from R3. In terms of n by n, a general notation, each vector is simple from Rm. So the maximum dimension that a column space can take is also Rm. But in this case, it won't be Rm. We already bring A to U. So from U, there are two independent vector. Oh no, not rows, because this is a row space. There are two independent columns that contains pivots, two free variables for second and the fourth column. But now, if we pay attention to only the columns, then the first column and the third column are my pivots. So they form pivot columns. As they are pivot columns, we can trace the information to the first and the third column layer. So the basis for this column space is 1, 2, minus 1, and 3, 9, 3. I have to emphasize this one more time. Don't take the independent columns in U and consider them as the basis of the column space of A. No, the column space of A has such a basis. Yeah, because only the two vectors here are independent. Basis of U is 1, 0, 0 and 3, 3, 0. And basis of A is 1, 2, minus 1 and 3, 9, 3. Different, very different. So how about the dimension? R2, right? It's R2. Yeah. RR actually, which is the same as the dimension of the row space. And that's not a coincidence, because the number of independent columns is always the number of independent rows. Yeah, so if a matrix that has a size of n by n and a rank of R, it has R independent rows. It has R independent columns. These are true for both U and A. So in this short course, we already see an interesting, oh no, not interesting. This is interesting, but that one is not. That one is basic and important and nothing interesting from basic stuff. A basic decomposition method called A equals LU. We can factorize A into two matrices. It can be done in a rectangular form, and it can also be done in a square case. A equals LU. L is always square. A and U have the same size. Now, the second factorization in this short course is A equals CR, where C contains only the basis of the column space, and the size of C must be n by R. Consider n by n as A. Yeah. C must be n by R. It is the basis of something. So not too many vectors, not too few vectors. They must be independent. And column space has a dimension of RR. So if we put those vectors as a matrix, we should select at most R vectors. We should select exactly R vectors. So C is C n by R. And the R part contains the basis of the row space. It must be R by N. So in this case, C can tell us the basis for column space. 235, 117 must be the basis for the column space. How about the question mark in the second matrix? Yeah, I leave them empty purposely because let's review the matrix multiplication. If we use linear combination for columns, then the first column in A is the same as only this column. So I have to choose 1, 0 for the first column, so that 1 times the first column plus 0 times the second column gives 2, 3, 5. Similarly, for the second question mark, 0 and 1. 0 and 1 will make 0 times 2, 3, 5 plus 1 times 117 equals 117. The last one is 3, 4, 12 in A. So 3, 4, 12 is 2 plus 1, 3 plus 1, and 5 plus 7. So clearly it's 1, 1 for the last columns. Yeah. 1 times 2, 3, 5 using the product of column. You can make a linear combination of 1 times 2, 3, 5 plus 1 times 117 gives 3, 4, 12. The reason that I find R is the basis of A can be found by 1, 0, 1 and 0, 1, 1. So this explains the basis of R, and that explains the basis of C. I call this interesting but not useful or important because it's just a fancy way to indicate the basis of column space and row space at once. We can see the basis just by this expression, a single factorization. But I would like to mention R as the kernel because M times R, M by R for C and R by N for the row space. This also connects the number of independent columns and the number of independent rows in A. The last subspace here is lemma space. To fully know lemma space, we have to borrow what we learned in null space. Null space means the x that makes ax equals 0. If A contains n columns, this linear combination makes 0 for the right hand side. It generates a 0 vector. The definition for lemma space is called the y that makes the linear combination here. The y that makes the linear combination of all the rows be a 0 row. But a vector must be tall, right? You cannot express vector as a row. So to do a row manipulation, the multiplication by the point of view of rows, I need a transpose sign for such a vector. So the y, let me put this clear and a better comparison. The y that makes the linear combination of the rows be 0 as all the entry in this row is called the lemma space guy. When this entries times this one plus this entry times this one until this entry times this one gives 0 for the whole row. This y is the lemma space vector, and the lemma space is defined or denoted by the null space of A transpose. Yes. So the null space of A means the x that makes Ax equals 0. The lemma space of A is also the null space of A transpose. So actually, I don't have to introduce something new. If you transpose A and make A to swap the row and the column, then the x that makes A transpose X be 0 is already the linear space. But this requires a transpose for A and do a Gaussian elimination one more time. You have to repeat the whole Gaussian elimination when A swaps the row and the column. So while we accept it, we already have the linear space. If we work toward A transpose, we are not satisfied with it. It takes just too many computation, and most importantly, it's not clean. It cannot connect what we have done, which is Gaussian elimination. So my point is, can we tell the linear space just based on Q or the result out of Gaussian elimination? Yes, we can. Because if you take a look for the definition of linear space means those entries which perform row operation or the linear combination of all the rows, which makes a row which has purely zero everywhere. So it further means that we have to find a row in U where it's perfectly zero. It's zero everywhere. Yeah. If we can find the coefficient that makes such a zero row, this coefficient shows how the combination of all the rows generates zero, and the coefficients fulfills the definition of linear space. So if we check all we did in Gaussian elimination, is there any row that is for the zero? We have seen one, we have seen many, but to generate a row full of zero is not uncommon at all. Yeah, it has to fulfill some conditions, but with 1, 3, 3, 2, 2, 6, 9, 7, and minus 1, minus 3, 3, 4 as 3 rows here. How do the 3 rows be synthesized into 0? Is there a coefficient shows the process of this one times 1, 3, 3, 2 plus another 1 times 2, 6, 9, 7 plus something else times minus 1, minus 3, 3, 4 equals 0, 0, 0, 0, which is here. It appears in the last row of U, but what is the coefficients that make such a linear combination? Where can we find such coefficients? L inverse. Yes, because it is the L inverse that brings A to U, so all the row operations can be found by L inverse. And this is why I keep saying that L inverse documents the whole Gaussian elimination process. They are produced by elimination matrices, and when we put those elimination matrices together, we see L inverse. So if you have L inverse, we have the coefficient that generates the zero row, and we have the vectors in the linear space. So let's take this as example. How do we see L inverse from U or the process that get U? Yeah, we won't see L inverse directed in U, but is there any chance that we can find L inverse fast? I mean, a slower way is to multiply those elimination matrices, like The first step is the first row times 2 and add it to the second. And the second step is the first row times minus 1 and add it to the third. And the last step is the second row times something and add it to the third row. We find those elimination matrices, we combine them together. Yes, this is a way, but it's too slow. It's too slow to go back to those elimination matrices and see the L inverse. A faster way we have dealt with is augmenting matrix. If we put B along with A and get A, B like this, then we can have the L inverse directly from the augmented part, the part attacked. For example, if you put A and B together and you finally get U like this, and most importantly, the new right hand side, C, such as this one, then the way to generate full zero row can be told by all these coefficients because it can be separated into 1, 0, 0, minus 2, 1, 0, 5, minus 2, 1, times B1, B2, and B3. So the last row shows how we get this perfectly zero. Here, if you use 5 times the first row, plus minus 2 times the second row, plus 1 times the last row, you have a row that is full of 0. And yes, this 5 minus 2, 1 becomes the null space vector without operating the original A transpose. You don't have to work toward A transpose, yet you can see the null space of A transpose, which is the left null space of A, which is the coefficient that generates a full zero row, which can be found in L inverse. But this cannot be done if you didn't attack the B along with A. It can, but it just be very complicated. It has to be found by multiplication of all the elimination matrices. This shows us the Leonard space. And in this case, the basis of the null space is 5 minus 2, 1, and it is R1. Dimension is R1. And the dimension of current space is R2, or RR in general. And the dimension for the left null space would be R1 or R m minus R. That's the dimension for left null space, R m minus R. And if you combine R and m minus R, we can see that each column is from Rm, like 1, 2, minus 1 here. 1, 2, minus 1 is a vector from R3, right? But current space forms an R2 subspace. The left space in this case is R1. It's an R1 with only one vector, R1. So fill the whole Rm. I mean, current space fulfill R2, R. Left space fulfills R1, m minus R. It's quite like the row space and null space case. In row space and null space, row space has a dimension of RR. Null space has a dimension of n minus R, and each x, or the row, is sample from Rn. So they fill the whole Rn, and in the last section of this short course, you'll see it's not a coincidence. You can see the information of null space from the nulls, then from the row space, and similarly, you can see the information of column space from Deleuze space. And actually, Deleuze space is just another side for column space. They are like complement. They complete each other. By combining them together, you see the information for all the Rn, Rm. So that's why I organize the four fundamental subspace as the topic in this short course. Because if you can fully figure out the four fundamental subspace, the next time you have a matrix, you won't bother this matrix by the entry level, reading them entries by entry. No, that's the amateur style. The correct style to interpret a matrix is not only by column. Yeah, I start this short course by identifying the columns and columns only. But now you already knew you can see the information of row from the column. So when you see the information of column, you already get the idea of row. But now I just extend this to something beyond. You can see the information of columns based on the guys that makes Y transpose A be 0. And you can see the information of row from the X that makes AX equals 0. So, I mean, when we generate a matrix, it's like we have so many degrees of freedom. I can fill in every entries based on my own my own preferences. Yeah, it's like I have my it's all controlled by myself. I select the entries. Everything is a this degree of freedom controlled by me. But no. When you assign these entries, you already determine the subspace behind them. You already determine what is derived and what the row structure and the column structure are. I will conclude this by providing an analogy in the end. But now let's proceed, and you have the same feeling as mine when you get the whole picture. Let's use some more example about finding the Leibniz space. How about the transpose one? I have transposed a matrix before, maybe here, right? And such a matrix produce two zeros in the row 2 and row 4. 1, 2, minus 1 here, and 0, 3, minus 6 here. And the second row and the third row are 0. So tell me the dimension for the Leibniz space in this case. And also the way to find the basis. Yeah, the dimension for the column space will be R2 because I have only two independent rows, which means I have only two independent columns. And there are 2 0 rows. So the dimension for Leibniz space in this case will be R2. Yes, R2. And I can find two vectors in the basis. And those basis vectors can be found reading the right hand side. Yeah, I don't repeat it here, but if you check those coefficients in the new attack part as an augmented matrix, you can see how we generate the 0 row. Yeah, for example, I believe 3 let me write down here. I believe 3 minus 1, 0, 0 is a Leibniz space vector because 3 times first row plus minus 1 times second row will be 0. Another can be found by the last row. I can definitely figure out a way to generate a 0 row there. So can we do that here? Yeah. How do we make a 0 row for the last one? It should be a minus 1 times the first. And how about the third row? Yeah, let me check. 1 2, 1, 2, minus 1, and 3, 9, 3. How do I get to 7, 4 here if I select minus 1 in the first place? Or something else, for example, minus 1 would be great, right? So minus 1 times this plus 1 times this would be 2, 7, and 4. So this further means the first row times 1 plus the third row times 1 with 0 for the remaining rows will generate a 0 row. So 3, minus 1, 0, 0, and minus 1, 0, 1, 0 is the basis in the Leonard space. Okay, and how about the current space? The current space in this case is 1, 3, 3, 2, and 2, 6, 9, 7. 1, yeah, let me put this in a clearer form. The Leonard space is found by 3, minus 1, 0, 0, and minus 1, 0, 1, 0. And the current space is found by 1, 3, 3, 2, and 2, 6, 9, 7. The first column and the second column, right? The last section is about orthogonality, and I would like to preview something before I formally introduce what orthogonality is. Could you find the inner product between any two vectors where one selected from the Leonard space and one selected from the current space? The inner product means we multiply the associated entries and we sum them up. So 3 times 1 plus minus 1 times 3 plus 0 times 3 plus 0 times 2 is a perfect 0. Next, how about this? If I find the inner product between them, 3 times 2 plus 1 plus minus 1 times 6 is also 0. Next, this minus 1, 0, 1, 0 times 1, 3, 3, 2 is also, again, 0. Finally, how about this? Oh, no, I forgot to put a minus 1 here because this is minus 1 times the first row plus 1 times the third would be 2, 7, 4. So to generate 0 for the right hand side, I should place a minus 1 here so that minus 1 times this plus 1 times this minus 1 times this would be 0. So if you perform minus 1, 0, 1, minus 1, and 1, 3, 3, 2, inner product 0. Similarly, the two, oh my god, if the inner product here is also 0, we'll officially call them orthogonal in the last section. But my point is, you can see the information of current space from the Leonard space, and their dimensions also tell us something. It tells us they fill the whole Rm. It's just like they fill the whole Rn for null space and row space case. So let's move to an example here. Yeah. So without computing, we already have the LU decomposition for A. A is LU, so let's find the basis and dimension for the 4 fundamental subspaces. For A equals LU, the basis of row space can be found by the independent rows in U, and as we have 3 independent rows, so 1, 2, 3, 4, 0, 1, 2, 3, and 0, 0, 1, 2 are my bases, the row space, and the dimension is R3. As for the null space, is to find how to make AX equals 0. So we have to break down the pivot variable and the free variables. So from the information there, x3 plus 2x4 equals 0. x2 plus 2x3 plus 2x4 equals 0. And finally, x1 plus 2x2 plus 3x3 plus 4x4 equals 0. So we can express the x that makes ax equals 0 as 1 for x4, minus 2 for x3. And if this is minus 2, then minus 4 plus 2 is minus 2. So 2 for x2. And finally, wow, this is beyond my computation. So it is 2x2 plus minus 3x3 minus 4x4, where x2 is 2x4, x3 is 2x4, minus 2x4 and 4x4. So finally this is 4x4 plus 6x4 minus 4x4, which is 6x4. So 6, 2 minus 2, 1 is the null space component. Yeah, the basis is 6, 2 minus 2, 1. And the dimension, how about the dimension? R1. So let's check whether the dimensions make sense. Row space R3, null space R1, and overall, each vector is sampled from R4, and they indeed fill out the whole R4. So yes, this is correct. When we go back to this slide, you'll see how we interpret orthogonal narrative from here, and how to check if we have missed something potentially. Okay, so the next one will be computational error from a verification, and this is why the verification is so useful. It should be minus 1, minus 2, and 1. I readily found what I missed because I already used the information in the last section here. This should be the null space vector. I beg your pardon, there could be some computational error when I simplify all these equations. Okay, never mind. So the basis for the current space is what? Can I simply put the independent columns in U? Because I just keep emphasizing that the independent columns in U tell us what columns to be independent in A. We should trace back to A and find those columns, forming them as the basis in A. But there is a shortcut here. I can't trace back to A because A is not explicitly provided. And the problem statement also needs me to find everything without computing A. But there are 3 independent columns, which means the rank of A is 3. And each column is sampled from an R3 space. So it's already full rank. This is like the R equals M scenario in the previous section. This also means that, yeah, I still can take the three independent columns in U to call them bases. But the base way could be just arbitrarily choose three independent vectors such as 1, 0, 0, 0, 1, 0, 0, 0, 1, or any three, you name it, like 1, 0, 0, 1, 1, 0, 1, 1, 1, anything. If you select three independent vectors, they are all the basis of the column space because the column space fill the whole R3, which also tells us the Reynolds space takes only R0. The Reynolds space takes only R0. It still has a vector. It's just the vector is 0. Yeah, it's an R0 space. It's an R0 point, a zero-dimensional point in the Reynolds space. So it's a bit tricky in this scenario. If the columns does not fill in the whole Rm, what should we do? In that case, there must be a zero row. Find that zero row and find how to synthesize the zero row based on L. So did I ever use anything here? No. This is just a lucky case. I didn't use any information because R is M, and I don't have to find that M minus R Reynolds space. If this one is purely 0, it's 0 everywhere, I have to find the inverse of it. I have to find the inverse of it and check the row that is matched to the 0 row. Those coefficients are put to the Reynolds space basis. I skip it. I'm lucky because it is a full ring case and the Reynolds space is R0 with only 0, 0, 0 considered. Finally, in this section, it introduced a spatial matrix called rank 1 matrix. In next section, you are going to see U transpose V is called inner product. U is M minus 1, V is 1 minus M. So when you transpose this into 1 minus 1, oh no, they are both M minus 1. So if you transpose this into 1 minus 1, 1 by M, then a 1 by M vector times a m by 1 vector is reduced to a 1 by 1 single number. It's no longer a matrix, just a number. So we call this inner product. And what I just did is to find the inner product between a vector in column space and a vector in the Reynolds space. So I have U transpose V as an inner product. You're going to see if the inner product is 0, then they are orthogonal. The two vectors are orthogonal. But UV transpose is something different. UV transpose is a matrix. It's a 1 by M. Oh no, if M is M by 1, and V is N by 1, which makes V transpose 1 by N. So M by 1 times 1 by N becomes a M by N matrix. But this matrix is rank 1. Yeah, it's like the building block in the matrix multiplication. Yeah. Because the UV transpose in this case can be found by first, U is 4 by 1 and V is 3 by 1. So UV transpose becomes 1 by 3, where the first row is 3, 2, 4 by 1, 3 by 1. So UV transpose is 4 by 3, where the first row is 3, 2, minus 7. And the second row is 3 times 3 to 7. This one is minus 1 times 3 to 7. And 27, 18, and minus 63. So if you perform Gaussian elimination, this must be 3, 2, minus 1, and minus 7, and 0, 0, 0 for all the remaining rows. It will be a rank 1 matrix because each row is found by the multiplier of the first row. And similarly, each column is found by the multiplier of each column. So it becomes quite a special case. You have a matrix, but this matrix is rank 1. Perhaps you are wondering, rank 1 is so redundant. If a matrix is rank 1, it seems that we get little information from it. This is quite the opposite. In a lot of real-world application, we would like to approximate a matrix by something lower rank. It has the same size with that matrix, but if you can use a low rank approximation like the lowest rank 1 in this case, originally that is a m by n matrix which contains m by n numbers. Concerning 1000 by 2000, you have 2 million different numbers, and to store the full 2 million numbers could cost a lot of memory. But if you can approximate that 2 million numbers as a 1000 by 2000 matrix into something low rank, like rank is 2, you reduce the rank from 1000 to 2, yet it is a good approximation, or even a rank 1 case, then you can approximate the originally 2 million data using only 3000 number coming from 1000 as a vector, 1000 by 1, and 2000 as another vector, as a 2000 by 1 vector. So 3000 in numerical numbers could potentially replace the 2 million information. So imagine how I compress the information from 2 million to only 3000. Yeah, that's almost 6% or no 0.6%. Wow, that's a 0.6% reduction. Yeah, but yeah, it depends. That doesn't mean every matrix can be done by this. But in real world, we ended a lower rank approximation if that is a huge matrix, and there are huge matrices everywhere in real world. So matrix with lower rank is usually our concern. Now, for example, if it is a 1000 by 2000 matrices, and you use a 1000 times 2, 2000 times 200 matrix with R equals 2 to approximate it, then 2 million information is reduced by only 6,000 numbers. Yeah. So low rank in approximation is of interest in real world.